Can you imagine trying to code a model, a hydraulic model, to run this and accurately produce the same results as you see here in real life? So in this presentation, what we're going to do is we're going to discuss some new cutting-edge procedures as well as some older procedures on modeling the hydraulics of stream situations such as this. We will demonstrate how these techniques and these procedures are used on a study that was performed for the city of Kansas City, Missouri on Indian Creek, a major tributary to the Blue River in the city. Hello, I'm Don Baker with Water Resources Solutions, and I was the project manager for this particular project. My specialty is in water resources engineering, particularly stormwater management and hydraulics, and as well as eco-restoration. Water Resources Solutions is a firm specializing in water resources, and we do specialize in four areas, including stormwater management, hydraulic structure design, including dams and levees, ecosystem restoration, and particularly stream restoration, as well as more holistic overall watershed management type work. This region of Indian Creek that you see here in the video was taken during a flood event in July and August of 2017. This region, or this reach of Indian Creek, was originally the location of a flour mill right there on the state line. The flour mill took advantage of a waterfall and the close proximity of the bedrock to the area. Interesting part of this stream is that the stream actually runs along a limestone bedrock layer, and so as such, as it gets deeper, what it's doing is actually eroding that bedrock. This area has a long-standing history of flooding. As you can see from the video, there's been encroachment on the stream by development, both residential type development, commercial type development. During these events, these were two rainstorms that occurred within a couple of weeks of each other. This is one of those rainstorms in 2017, and produced flows that were significant in the creek, however, not what the city or the folks around here would actually expect to see in kind of what we typically use as kind of our benchmark for maximum flood event, the 100-year or the 1% annual exceedance flood event. One thing that became evident from this event is that the current state of the modeling that the city had with regard to its FEMA flood models did not accurately reflect what was happening in real life. While this flood was significantly less than the benchmark 100-year event, there was flooding that was occurring to locations that were not identified on the FEMA maps. And likewise, locations that were expected to flood didn't flood. And so this the issue that the city has is that they're trying to manage with a set of flood maps and a model that don't accurately depict the real life situation. So Kansas City, Missouri is a newly minted cooperative technical partner with FEMA, which basically means that they're in the process of managing the mapping in the city in association with FEMA, and in an effort to try to get better mapped floodplains, so that basically that results in easier floodplain management for the city. While you saw in the footage here that this part of Indian Creek has been developed, both residential and commercial, there is still a lot of pressure through this area to redevelop it. And so having good floodplain delineations, good mapping, and good modeling information will make it easier for the city to manage that development effort and to ensure that folks don't build things in the floodplain where it will impact significantly, perhaps, the safety of the public. As Kansas City, Missouri looked for opportunities to fund their project, they started working with the Corps of Engineers, which has a program that is called Planning Assistance to States. And what this program does, this allows the Corps of Engineers to provide funding to study problems such as this. So once this funding was in place, Both the city and the Corps of Engineers looked to the design community or the AE community for folks who had expertise in hydraulic modeling that could really do a good job with respect to this. Water Resources Solutions had a good relationship with the city and working with city staff, some of whom we worked with for a couple of decades. Also being a contract holder with an indefinite delivery, indefinite quantity contract with the Kansas City District, Water Resources Solutions was chosen for this project primarily for its hydraulic modeling expertise, but also the fact that its relationship with the University of Missouri Kansas City and doing physical models over the past 7 or 8 years. This expertise in physical modeling worked very well with the city's plan for this particular area. They had the intent that they wanted to use a physical model to help as a sort of demonstration project on the usefulness of that particular modeling technology. So Water Resources Solutions over the past 8 years has been in the process of developing a modeling methodology that incorporates not only numerical computer modeling, but also physical modeling. Traditional physical models efforts occur where you actually do the computer modeling first and get the results of that as kind of a basis or an existing condition, and then you build the physical model after that. As we worked through these projects over the last 8 years, we actually found out that by doing the physical model first, we were able to help define some of the boundary conditions and some of the unknowns and some of the flow patterns and some of the assumptions that are inherent in the computer models, and help define those so that the end result of the computer model was actually more accurate. And so as a result, we've developed this concept that we call physical first. Okay, so there are several advantages to this physical first approach. First of all, clearly it uses both physical modeling as well as numerical computer modeling to get to and arrive at both an answer and a solution. The physical and numerical models clearly are different, but they both have their strengths that we play off of one another here. The physical model, while doesn't necessarily give us some of the detailed, down to the decimal point accuracy of velocities and flow elevations, what it does is it really helps define and helps us understanding interactions with the physical environment, such as infrastructure or geology or other things in the floodplain, other riparian areas and things. And so its strength helps us understand and physically see those flow patterns that are more difficult to see in the numerical model, which has the strength then of very accurately calculating velocities, flow rates, flow depths at specific locations, once the information and the assumptions that are put into those models have been calibrated to what we're seeing in real life. So some of the myths about creating physical models right off the bat is that it's very, very expensive. A lot of folks also believe that it's old school, that we don't need to do that anymore because we have tremendously fast computers and we can model everything with computers. The models must be large and cumbersome, and you have to have big spaces to construct them. And that it's very limited in that you can't physical model every situation. And so those myths are definitely not exactly true. What we have found is that from an expense standpoint, we're able to build, and a size standpoint, we're able to build models that are that can fit in a normal sized laboratory. The majority of our models over the past 8 years fit in a regular university laboratory. This particular model is a little bit larger, but that's only because we were modeling a very long extent of the Indian Creek on this. more traditional physical models that are built to larger scales certainly do take up more space and are more expensive. But based on this idea of a kind of a mesoscale model that we've developed, we get really, really good results and really, really good answers with a model that doesn't have to be that large, that expensive, or that cumbersome to use. It's important to remember, physical first is literally physical modeling first. And so the physical first starts with the idea of building that physical model. So for this August event in question, that's in question here, there were several questions that were raised about the hydraulic models that existed for the creek at that time. And one of those is they did not seem to, indicate the flood extents accurately. There were also questions about since the existing models were one-dimensional numerical models, there was not a lot of information about flow patterns and how the water actually ended up where it was physically observed later on. And finally, the real main question is how do we create a model that accurately depicts the situation so that the city can use that for really good planning purposes. So as far as our process for this model, breaks down into several different categories. The first one is really understanding the area that we're modeling, and so that includes some field evaluations, some site visits, actually walking the stream, collecting all the available data that we have, particularly all the mapping data. Fortunately, we're in a world now where LiDAR data is readily available to us, and it's good solid LiDAR data that's accurate. Of course, we need to supplement that with some physical topographic survey, and so we had surveyors actually go and do that, particularly for underwater shots, getting the bathymetry under the water so that we accurately depict the channel bed. Historic information on the flooding, which included old reports. It also includes photographs of high water marks so that we know where we're calibrating to, so we're making sure that the results of our modeling meets what was actually physically observed. So then once we have all that data collected, then we move into the next part is the hydrology. How much flow is coming down through here? We're going to look at land use patterns and rainfall. And in this particular case, fortunately, we had a U.S. Geological Survey stream gauge right there. Part of the detriment is that when the flood reached its peak, the gauge was inundated and ceased to accurately report the information, the data. But we had good, solid stream information up to that point that we could calibrate to. And so once we understand hydrology, we understand what flow rates we have available to us, what we're actually modeling. Then we begin to actually start creating that initial physical model. Before doing that, we do run and take the information from typically a one-dimensional model that exists for in this particular case, the FEMA model. While it did not accurately depict the flood extents, there's still valuable hydraulic information in there that we can use for our physical model. Okay. So as we begin our physical model development, the steps that we have to go through have to do with the scaling considerations. And once again, like I said, is we want to create a model that is large enough that it accurately depicts the flow patterns and the flow depths and the velocities, but not so large that it's cumbersome and we need extremely large areas to build it or extremely large pumping plants to pump water through it. And at the same time, we also don't want it so small that we actually start getting into other hydraulic characteristics that will actually affect all of those other parameters we're looking at. If we start getting it too small, the best way to think about it is if you think about surface tension effects. If you get water too shallow, or water that is interacting with the actual model material, and the friction is too great, we'll get erroneous results. So there is a balance there. We also start looking at the hydraulic information. Once again, what does the roughness look like? What does the terrain look like? How do we do that? So we use the LiDAR information in addition to the bathymetry information, and we actually create a surface that we will use to build the model. Now it's time to start constructing the model. In this particular case, for the city actually owned the building in which they were going to allow us to build this model. It was actually a section of their building that used to be an old welding shop. And so we had plenty of room. In this particular case, it's a little bit larger than a university laboratory, just because of the extent of the model. And however, this particular location had all the electrical power we needed, had all the water supply that we needed. And so we were able to fit it in here and keep things contained without a great deal of effort there. First thing that we had to start building was the base and the frame. And so you'll see that as we go through. The video here, this particular model was approximately 80 feet long, approximately 40 feet wide. And so that particular effort took a little bit of time to create. The terrain creation is something that was a little bit new on this particular model. In the past, we had often done a lot of the terrain creation by hand for our smaller models, but for this larger model, that just simply was not going to be a good, viable solution. And so as a result, what we did is we used the surface that we created from the LiDAR and scaled it down to the dimensions and the scaling of the physical model. And then actually had it computer numerically controlled, routed. So basically you feed that surface into the computer, and it actually runs the router that actually routes out building insulation foam. This building insulation foam that we chose here was a little bit denser than is commonly sold at your local hardware store. However, was still readily available, and the denseness of that foam served a couple of purposes. One is that it was able to stand up to the routing without fraying and coming apart in that process. But also the tightness of that foam would help us later on with our water tightness. Once the panels were routed, these were 4x8 panels that ranged anywhere from 2 to 4 inches thick. Once all of those were routed and accurately labeled, of course, the layout started commencing. And so basically we started laying out the panels and laying them together. At the same time, making sure that they fit well together, and then starting to glue them in place so that they wouldn't move. After we got things fit together, and we're confident that things were going to fit together nicely and lay out on the foundation or the frame, we laid a rubber membrane down on the base, and this rubber membrane was to capture any water that was to seep through the joints of the foam, and help keep it controlled so that it just didn't run out onto the floor. So once that rubber membrane was laid down, the model was reassembled on top of that membrane, and that's when it was final glued. Everything was then glued together, and all the cracks were caulked and fit together. The next step then was to how do we create the buildings? And so we did that with a similar process. Basically, the buildings were identified off of the mapping data that we had, scaled to the scaling of the model, and then were routed out of the same foam. Having the actual coordinates of where these buildings were to lie, we were able to accurately place them on the model, and we built them as separate entities. so that we could actually remove them, because one of the things that had occurred there post flooding at this location was that the city had demolished one of the strip mall areas that had flooded. The next step was to create the bridges, and so there were 3 bridges that are affected and that exist on this reach, and so the bridges were actually constructed or drawn from as-built drawings and other dimensions and some survey dimensions that we had collected as part of the initial data gathering. And then these bridges were then scaled and sent to a 3D printer. And so by 3D printing these bridges, we were able to once again accurately depict the dimensions, depict the geometry of the bridges, and then we would in placing the bridges in the physical model, because they were at the same scale, they would actually fit in with the terrain that we built. Once all this was done, the model was painted and sealed, so to prevent to actually create water tightness. One of the things about physical modeling is that there's always going to be leaks. However, you want to try to minimize those just from both from an aesthetic standpoint and a useful standpoint when you invite folks to come look at it, and at the same time also just from a safety standpoint without having a lot of water on the floor. Once the model was painted and sealed, we turned our attention to our pumping plant. In this particular case, since this was a new site, we didn't have a pumping plant in place, and so we ended up building this pumping plant on site. And so basically this consisted of a large water tank. The pump we had chosen was a 3 horsepower pump, and a lot of PVC pipe. And so with various valving and things, we were able to create a situation where where one pump would actually be able to both supply the water to the model, as well as pump the water out of the model at the end and back into the tank or down the drain. Once we had all this up and running, we now have a physical model. And so this physical model, the initial shakedown test, if you will, was completed by just running a series of flow events through the model to see how it reacted, to see if there were any leaks, to see if there were any issues that we noticed that didn't make any sense, and to go ahead and correct those. In this particular case, the shakedown test went extremely well. We did not actually have any major problems. And so that allowed us to very quickly move into the calibration phase. And so this is where we actually start looking at the velocities and elevations. And this is where we actually start looking at the velocities and the elevations that we see in the model, in the physical model, and then comparing those to a numerical model. So at the same time as this physical model is getting complete, we have now started creating that numerical computer model. And once again, or similar to the physical model, it went through a shakedown test as well. Once it was up and going, we ran it to make sure that it ran, and then got some initial results. So now is when we start comparing those with the physical model. So looking at observed flow patterns and observed water elevations and velocities. We actually did take measurements of velocities in our physical model using a pitot tube. And then going back to the computer model and seeing what differences there are, and then trying to explain why. And in some cases, what we see is that the computer model can be a little more accurate, if you will, or more detailed. Maybe accurate is not the right word, but more detailed in its analysis. And so that can actually show some differences. But a lot of other times, what we see the differences are in the physical model is showing those interactions with other physical features, other infrastructure, other geometries, other just flow regimes that are occurring in real life that just aren't necessarily part of the assumptions of a numerical model. And so with that information, we're able to change some of the knobs, if you will, in the numerical model and fine tune those. A common one, it has to do with the roughness coefficients and things. We can change those and say, you know what, instead of the traditional roughness coefficient, it needs to be a little higher, or it needs to be a little lower, and that sort of thing. Okay, so with the results of our model, after all was said and done here, and after all the calibration and combining where the two models ended up agreeing, the results of this model achieved the purposes of the project, where we were able to delineate the areas that were actually flooding, and it ended up, we were able to then match both the numerical and the physical model to what was physically observed on the flooding event back in August in 2017. We were basically, we validated and actually improved the numerical simulations that we had. Other purposes of the model, though, and this is an extremely important one, advantage to physical models, is that in the physical model we're able to very quickly test potential solutions. And so while this was not necessarily part of the original scope of services, what we were able to do is we actually did test a couple of solutions in the model by very quickly modifying the terrain. And in doing so, showed the effects of those improvements. For instance, at the Warnell Bridge in the downstream end of the project, what we're able to do is, what happens if we extend the opening of that bridge? If we made the opening of that bridge larger, does it help? Very quickly in the physical model, in a matter of a couple of hours, we were able to do that and run it and show that, yes, indeed, that actually was a viable solution. So that's one of the strengths of physical modeling. What we ended up finding was that there were flooding of homes as were depicted in the drone footage from the actual event. We actually showed that was true, and that it wasn't necessarily showing up in the FEMA models. Part of the shopping center that was there flooded, although the FEMA model predicted that the whole thing would flood, and we were able to explain why that was. We were also able to explain a convenience store located right next to the creek that had been more recently built than the rest of the neighborhood, and showed the effects, while that store didn't flood, showed the effects of its building pad and how it diverted flow around the building and actually sent water in directions that people weren't necessarily expecting. And so with that, we were able, like I said, with the physical model, we were able to show a lot of these different things. And we could do that very, very quickly, much more quickly than we could if we had to recode the numerical model for each one of these alternatives. All right, so in conclusion, why did we do this particular physical first process and using a physical model and a numerical model? Well, the advantages of this process to the client really comes down to expense versus value. What we're able to do is we're able to model a lot of different simulations and a lot of different ideas very cost effectively. What we have found over the years in doing these models and in this particular process is that there's always an aha moment. There's always something that we see in the physical model that we didn't expect to see, or that there's an explanation that comes out of that we didn't understand originally looking at the numerical models or even viewing things out in actual physical space. More importantly, using this process, we have always saved the project's money. In one particular case, we saved the project 67% of its original budget. That's sort of an extreme, but we do see on average that we can trim and save usually on the order of around 30% from original project budgets. And the reason for this is that we reduce uncertainty. We answer a lot of questions with physical models, and as a result, that those answers translate to the design of the project. The design may not have to be as robust as if you were trying to design for something that you didn't completely understand. And so that is really the power of this process, is to make a better, more defined project that is more focused, with fewer uncertainties, less risk, and as the end result is that the clients save money with this process overall. So the value of these physical models is the fact that you can actually feel and touch them and see them. One of our models that we did was actually geared entirely for that purpose. It was actually built outside in front of Linda Hall Library, which is a big private engineering library here in Kansas City, of the Panama Canal. And it was really meant for kids to interact, and we had actually little motorized boats and a working lock and dam system. And that particular model stayed out in front of the library from spring into the fall of that year, so that people could interact with it. As such, this was originally supposed to be an on-site tour, and so with this being now a virtual conference, we couldn't do that. However, we would like to invite you to come and tour our physical models, if not this one. We do seem to have a steady stream of those occurring, and so anytime you're in Kansas City, if you'd like to see a physical model, please let us know, and if we have one available, we will certainly love to give you a tour and show you how it works. We thank you for joining our presentation. We hope you found it informative and interesting. If you have any other questions regarding the presentation or any aspect of the project, our contact information is here on the slide. You can contact me here at WRS at dbaker@wrs-rc.com.